Good, thanks all for being here. Today I'm going to be sharing some work at the foundation of decision theory, where we try to think about what it means for agents to learn in ways that are typically not accommodated in the classical decision frameworks with which we're familiar. This is collaborative work between myself and Alex London, who's an ethicist, and that's a very interesting conversation to eavesdrop in on, where we sit down and try to translate between our worlds. That said, I'll say that the idea, the kernel of the idea, is from Alex, in the sense that Alex approached me and was like, I want to be able to talk rigorously about processes like when you go to therapy and you're in conflict with someone, and you're told by the therapist, I want you to reflect really on the options available to you. And you might have started off with an ask of, you know what, I need you to not hang out with your friends on Sundays, right? And then, so the options are hang out and not hang out. But then you think, well, are those the only options? Maybe there's a version of like, I still hang out with friends on Sunday, but we make sure that Tuesdays and Wednesdays we have time together, or something like that. This kind of this pattern. So we looked at the possibility space and we took one of the options and we thought more deeply about it. And in that sort of a reflection, we're able to find, right, some kind of a value that wasn't immediately obvious. And then he kept approaching me, and Alex is very used to dealing with all the mathematicians and formal epistemologists at Carnegie Mellon, and he's like, make me some math to do this. And so this is the kind of product of that effort to try to capture these sorts of learning experiences. So another way to state the motivation is that standard decision theory treats uncertainty about facts, but fixes values. In particular, it addresses problems of rational choice over fixed sets of acts with known probability and utility functions. That's our classical setup for rational choice. But we might want to be able to entertain more basic uncertainty about our representations of the world. Right? Our models, our conceptual spaces, when we set up and think, what are the acts available to me? What are their values? Right? What are their probabilities? I might want to be able to accommodate that within this framework that does so much work for us in other contexts. In particular, as bounded agents, we have not typically thought through every precise and particular way we could realize our actions. So like the couple in therapy, we might not have thought through every way that, don't spend time with friends, right, or do spend time with friends might be fine-grained, right, or realized. Now, this matters, of course, not just because we want to understand what's going on in therapy, but because presumably both we and the artificial agents that we're designing are precisely in this situation. We have not considered every possible realization of our actions. Right? And right now, in the current framework, we can just say, fix those, make a choice. Right? What we'll see is that to try to model this sort of a different learning experience, right, we're going to use the Jeffrey Bolker framework and extend it from the normal context of kind of epistemic uncertainty and prove a sort of value of information theorem for this more robust sort of uncertainty. You might call it axiological uncertainty, you might call it, broader representational uncertainty, right? And in multi-agent settings, we'll go on to kind of establish that this sort of refinement has kind of characteristic effects under the right sorts of assumptions. Namely, we'll see that it will tend to transform zero-sum interactions into positive-sum ones. Right? And it'll tend to yield Pareto improvements in Nash bargaining. So I'll also give you conditions under which you might not want to do it. But the aim, if this kind of overall project makes sense, is to broaden the applicability of, right, the familiar and robust machinery that we have from rational choice. These kinds of cases where maybe, for example, we want our AI to say, I don't think I've thought through how to realize, right, the best act, or I'm uncertain of how to evaluate the act. And to reason about things like, when should I, as an agent acting, right, on behalf of a principal, pause and actually just think more deeply about how I should evaluate acts, right? How I should represent a decision situation before I go ahead and act, right, as though I have it all settled, right? So let's start with a fruitful vignette. Daniel's the Daniel name. In my articles, if there are ever witty titles, those are from Daniel. So, consider two agents, right? The arborist and the baker, henceforth A and B, they run into an orange, right? Initially, they represent the situation as split the resource or fight for the resource. And maybe even they evaluate these as kind of comparable options. Maybe kind of splitting of the resource is some value that's intermediate, but fighting for the resource at the prospect of getting all of it makes them comparable. Neither seem great. Now, one thing they could do is, based on this representation of the situation, go forth and choose to fight or split. Right. But another thing they could do is step back and reflect on whether that really is all the ways that they could fight or split, whether this exhausts, right, really sensibly the acts that are available to them. Right. Perhaps they step back and reflect, and as they think through it, they're like, well, there are actually different ways that we could split this, and the arborist prefers the rind for baking, and the baker prefers the meat of the orange, right? I'm sorry, the flip. The arborist prefers the meat, or say propagating the orange. They get the seeds in there, they get to make more oranges, and the baker prefers the rind for delightful delicacies. Right. Here they're actually getting the right part of the orange. So we might step back, refine our act set, and say, actually splitting can be resolved into finer grained realizations of splitting. In particular, we can not just chop the orange in half, but we can get all the rind to the person who wants it, and all the meat to the person who wants that. So how do we model just that sort of an interaction, that sort of a learning experience where these two sat back and thought about one element of their act partition, split, and thought through different ways that splits could be realized. And realized that maybe if you got a new ordering or the values over acts, now we have fight and split at about equal, but this kind of more resourceful version of split, that's better. And perhaps they could think through other divisions and they'd find like maybe the opposite allocation of the meat to the baker and the rind to the arborist is strictly worse than both of these. So how do we model this sort of thing? And we can ask in this, for this sort of account, to answer questions like, when should agents refine their act set? Versus when should they just proceed with action given a particular representation of the problem? So as mentioned, for our model, we're going to be using the Bolker decision framework. Here, acts, states, and consequences are typed the same. They're propositions in an atomless Boolean algebra. And the virtues of this is that then those propositions can be indefinitely refined. We can just keep asking, yes, one act is split, but can you think more particularly about split? Can you refine it further into split and you get the meat, I get the rind, split and we give it to a third person to divide and I split and you choose, I pick, and so on. And this is kind of distinct to Jeffrey Bolker relative to the standard decision frameworks. If you can compare V&M or Savage, right, both the acts are typed as different from their equivalent of states, right? In V&M, acts is just, right, to take an act is just to make a choice of lottery. And in Savage, right, acts are functions from states to consequences. And further, in places like Savage, you have to assume act-state independence. Right? So for things like the sure thing principle, one of the axioms of the Savage framework to make sense, you need it so that your acts and states, right, are independent in the appropriate sense. Which is also why, in the kind of Jeffrey Bolker's great PSA, you can't represent fundamental problems like what does it look like to put two agents, say a causalist and an evidentialist or UDT agent, in the same decision problem. Because the decision problem itself is specified by the choice of that independence relation. And if you're, say, the EDT agent, you said the right sort of independence is evidential. And if you're a CDT agent, the right sort of independence is causal. And that needs to be fixed before you enter the problem. And so in Jeffrey, we're able to actually do things like embed these agents next to one another, have their actions be propositions just like anything else, so just like states of the world, right, that they can learn from and condition on, right? They're not this other thing, this function, right, that's typed differently. And further, they're partition invariant in the sense of, right, if I'm doing my expected value calculations, however it is that I chop up, right, that algebra, it will yield the same answer. So for these reasons, this is a particularly congenial framework for this sort of project. It lets us indefinitely refine, it lets us model act-state dependence, which will matter for things like actually strategic interactions, right, where characteristically you expect your act to be dependent or on the state and vice versa. So if you're doing a sequential game, you expect the action of the other agent to be dependent on your current one, or if you're thinking of solution concepts that involve common knowledge, right, then there's this dependence via the mechanism of common knowledge, whether it's through correlated equilibria or through like the unstated ways in game theoretic analysis that we just say you happen, right, to share this particular cognitive state, right? I had actually a colleague who, when I showed these results to them, got very excited and was like, I want to do a version of this in Savage. And for the next few weeks, they just kept calling me up and being like, I think I've got it. They're like, I don't. They're like, this is so hard to do in Savage. I think actually you can, in principle, get the machinery of something like, right, a Savage style decision framework to do this, but I think it would be quite hard, and it would look quite ugly.
My other question, doesn't the Jeffrey Bolker have something equivalent or similar to the sure thing principle?
Mm-hmm.
That's
right. Each of them will have something that looks independent flavored in their axioms. Yeah. But this will not require that your decision problem already stipulate independence.
Okay.
And that's how it's different. Yeah.
And this is a very, I can't picture the sample space for atomless sigma algebra.
So think at this very coarse grain level, and I think it's actually one of the really nice features of Jeffrey Bolker, is that it can really capture how we intuitively think about our representations. So you're starting off and you're considering right now like attend, don't attend. Right? Just propositions in your algebra closed under the appropriate operations. Right? Now, you could think a little bit more fine grained, and you could take, right, a refinement of that proposition, which will just be a subset of that proposition.
I can imagine fine graining. I just can't imagine fine graining all the way down. I just need an example of the sample space that would. Is it like point free?
It's point free. That's the exact. The atomlessness, right, is the key property.
What is point free?
Point free. Point free.
Point free.
So you don't necessarily need something like the real numbers at the bottom of it. You don't need to be like, this is an exact possible world.
Right.
This is something that admits indefinite refinement. Now that said, there are formal ways to make Jeffrey Bolker look like it has possible worlds. And this is through the use of ultra filters, and Daniel knows quite a bit about this topic. And it's thought a lot about kind of interesting puzzles that happen when you think deeply about that sort of representation. Yeah, Paul?
Okay, so then this algebra is not well-founded. That worries me. I can't quite put a finger on why.
What do you mean by well-founded?
You have infinite descending chains, infinite descending sequences of containment. I'm not quite sure why that worries me, but it does.
Think of it as the sort of thing that you might want if I'm representing your conceptual space. And roughly what that says is, I just want to allow, operationally, for you to keep thinking, right, more deeply about a proposition. It's not now, it also, I think, as a matter of interpretation, suggests the interpretation, which is, this is about an agent's perspective of a situation. As opposed to sometimes the other interpretation is, right, the sample space is like this deep ontology of the world. Each point in that sample space is a possible world where every fact about the universe is fixed, right? So this is not pointing at that sort of a picture, right? So that's why I think you...
No, I've changed my mind now. It looks like this is, you're adding additional constraints, additional facts about things. I don't think I quite got that right, but the base of that well-foundedness hierarchy, question marks, would be the entire algebra itself.
Yeah,
There's
it goes the other way.
Conclusion reversal, there we go.
Yeah, and so think, interpretationally, don't think this is a commitment to possible worlds being infinitely divisible. This is just a kind of operational feature of how I want to represent you as being able to continue to make indefinite, right, refinements of your representation. Right. So, in the literature, the closest thing to what we're thinking about is something called awareness growth. And this is typically done in the context of thinking through Bayesian reasoners and how they might change their model of the world. And in fact, Joyce has done something that's going to be close to what we're thinking about, but with important differences that I'm going to highlight. So in the fourth chapter of the Foundations of Causal Decision Theory, Joyce lays out his model of awareness growth, right? Where you can time index your epistemic state at a time, right, with a sample space, an algebra, right, and a probability function defined thereon. And Joyce observed that in the standard Bayesianism, you have a fixed algebra, right, but we want to allow this to grow. And for Joyce, there are two types of growth: refinement and expansion. Just as a kind of important feature of the framework, Joyce has it so that there's a canonical embedding of your first algebra into any future algebra. That you're very rigidly constrained what is allowed to happen to your credence function, which is the one object you allow us to reason about. Right? In particular, you're going to get things like all conditionals are preserved, and that appropriate likelihood ratios are preserved as well. Right? So for refinement, Joyce has it go as follows. Take an element of your algebra and partition it. And then he has this kind of disaggregation kernel which assigns the conditional probabilities to those elements of that proposition, right? Of the partition of that proposition, the Cj of C, right? Where, because this is not like a conditioning experience, this is a different sort of creedal attitude that you have that now just divides up, given that I'm in, right, split the orange, what happens to the different ways I'm thinking about splitting the orange. Right? In particular, you can just think of it as you move from your algebra at time t to an algebra at time t plus 1, and the relationship will be that the original algebra will remain a sub-algebra, right, of the refined algebra. Yeah.
So to refine, you have to specify two things, namely the partition and this k.
That's right.
Okay. All right.
Yeah. They turn it off. has this been done?
Just use the top button.
It may be out of power.
I also have one, actually. Forgive me, I really enjoy the mobility of walking around anxiously while I talk.
So we have like kind of at least, but expansion and refinement are kind of orthogonal to like usual Bayesian updating, right?
That's right.
Okay.
That's right. Bayesian updating doesn't tell you what to do in these kinds of
Yeah,
things. You can think of these as introducing a new kind of learning experience.
But importantly, there's like a connection because you're never contradicting what you knew before. You're kind of always expanding what you know, but you're assuming what you knew before kind of remains out there.
Exactly.
So you have this inclusion map, I guess you can set, you're also allowed to update your probabilities over them, so you can just set some to 0 if you want to exclude them.
Right, but that has to do with new evidence or something, right? You have to get...
Yeah.
Good.
Yes.
So, visually, what does this look like? Refinement looks like the following. I have a proposition in my algebra. Right. I introduce a partition of that proposition with the weights determined by the k function. The next form of awareness growth for Joyce is expansion, right? Where we introduce new disjoint possibilities, these deltas, where now we just take the union of our sample space and this new possibility. And again, just as you're saying, Riff, for Joyce it's important that this doesn't touch anything about our initial beliefs. Right? We're going to preserve all of our old ratios in terms of conditional probabilities, and we're going to scale up in the sense that if you carved out some part of the probability space, for this new thing, everything else will shift proportionally.
What's the iota operator?
Yes, that's from the mapping of the first algebra to the second. That's the canonical mapping of your algebra at time t1 to time t2. And so what does this look like? This looks like actually just introducing a totally novel disjoint proposition to your sample space and thereby to your algebra.
Can you show the previous slide again? So the scale, so scaling just as like propositions in delta t have like solve their own like probability, and therefore you like normalize it again.
Exactly.
So, is there actually a difference between refinement and expansion? Or can you just say, actually, I've just split W2 here into two parts called W2 and delta T?
Let me think about whether you could formally do that. I'll show a sense later on that you can subsume expansion into a case of refinement.
Okay.
That's not exactly what you're saying, but it's in flavor close to it.
Right.
I think if you carved off a piece of W2, you'd have some kind of questions you'd have to resolve about those proportionality issues.
Yeah.
Right.
Right.
Ah, sure.
You wouldn't
Yeah,
consider it.
yeah. Okay. Right. I see what you mean.
Good. As mentioned, the conditional structure is preserved, and we only change the domain of propositions in this picture of things. So, this is, I think, an interesting step. That said, where it leaves off is that it only touches probabilities, it doesn't touch utilities for an agent, right? And also makes it so that this interesting sort of a learning experience, doesn't affect anything from beforehand. It doesn't affect the proposition that was itself coarse-grained or refined, or anything like that. And if you kind of go back and think about our learning experiences, things like, I was at the therapist, I thought through how it is that we would split a resource, or you'd allocate your time. You might want it to be that it's not the case that when you're done evaluating that proposition, it leaves nothing else untouched. Like there's no learning experience that when you thought carefully through how to divide up the orange, would change either your value or your credence of any other proposition happening. Like imagine you thought through, like, if I divide up my time by giving you Saturdays in the proposition, don't, or do spend time with your friends, but then spend these extra days with me. Maybe that taught you about the other world, where you do spend time with them. Like, it's perfectly plausible that you have learning across the elements of the partition. Right? It's also perfectly plausible that by the time you're done evaluating it, you're actually all the options for me not spending time with my friends are not that good. I thought them through, I refined them, right? And all of them were worse than I thought, right? Like, that's the sort of a learning experience, right, that we might want to be able to model. It's not this thing that, like, when I learn my probabilities and utilities for the original proposition I learned about more deeply, thought about and considered and reflected on, can never change. Yeah,
I want to make sure I'm following because, so the Joyce model kind of ignores values completely. It's not about utilities.
That's right.
It's just about probabilities of events or something, or like refinement of an action space.
Yeah.
Then you kind of want to introduce this notion of, so you want to work on values. That's kind of the key thing in this talk. And you were saying like a possibility where when you think about things differently, like you realize like all these options are worse than I thought. That doesn't feel like a refinement, that just feels like a straight up change of values. So are you modeling something where like if you do more computation, it's just possible the values of the acts you had before might change, or estimates might change?
That's right.
And that's not refinement though. You're also going to introduce refinement of values kind of as a separate notion? Or
let's see how we land.
Yeah,
These are going to come, in the Jeffrey Bolker, they're going to come together.
All right, great.
In the sense that acts come with their probabilities and their values or utilities attached.
Okay.
And we're going to have the learning experience. It can be one that you just set up the constraint and say, this happens to be the special case of a learning experience where no matter what I could learn, it wouldn't change my sense of the probability of the event. Like if you're like plan A and plan B, you think through plan B, I could stipulate that no matter what I learned in my thinking in greater detail about plan B, the probability of plan B wouldn't change. That's a special case. I don't want to be restricted to that case.
That's fine.
So how might our valuations change is one question that we're going to pose. What if our probabilities also change? Right. And what attitudes are rational toward these learning experiences, right, of awareness growth? So these are things that Joyce does not consider. He does not consider values, just as Riff said. He does not consider probabilities at all being able to change of the original, right, say refined.
Well, I mean, the probabilities.
That's right, they change in the sense that they scale.
Ratios, yeah.
Yeah, they change in a very restricted way. So you rule out those more substantive learning experiences. And he does not talk about what should be our attitudes towards these sorts of learning experiences. Like if I propose to you, is it a good idea to talk to a therapist about alternatives? How would you evaluate? Like, no, I do think that thinking through the options is a good idea, or a bad idea, or not worth my time. Right? I want to be able to talk about those sorts of attitudes. So let's modify Jeffrey Bolker, right? But starting with the ideal agent, right, who's equipped with the following representation of a decision problem, right? A decision problem for our Jeffrey Bolker agent is going to be encoded by her complete bottomless Boolean algebra, right, which has all those nice properties that we talked about. An act partition, right, in which she chooses, in a sense, which element of this to realize by taking an act. And a utility function and defined over those acts, and a credence function defined, right, over the algebra. Or rather, the utility function is also defined over the act. You quotient out the bottom element. Right.
Wait, I thought there was no bottom.
There's a bottom element.
But no atoms.
Yes.
That's right.
Right.
You still get the contradiction. You still get the empty set.
Right. Sure.
Good. So we'll say that an algebra is atomless just in case for every element of that algebra there exists another element of that algebra such that it is distinct from the original and it is a subset of the original. This is this indefinite fine graining property. Right. And we see that the algebra is complete if for every element, right, it has a supremum and infimum in the algebra. The first axiom for this kind of a Jeffrey Bolker agent, and I'll move through these kind of quickly, is just to get the basic logical structure. As was asked earlier, you're going to get to see like the equivalent axioms here as you might find in Savage.
Sorry, the completeness, supremum and infimum in the algebra, what does this mean in this context? I don't understand. Any element has an infimum and supremum?
Every set, any subset of the algebra,
Oh, got it.
under the ordering of the algebra.
Okay.
Wait, say that again? Any subset of the algebra?
Yeah, any subset of the algebra will have an infimum and supremum that's in the algebra. Under, there'll be a greater, lowest upper, least upper bound, greatest lower bound.
And you can think of that you can continue to engage in logical operations and talk about things like, right?
Wait, what, I mean, what,
You can talk about it.
So the infimum of A prime, would that not be an atom?
Yeah, because it's
yeah, that's what I was trying to, thank you for asking what I was just thinking to ask.
No, it's
No?
What is it?
How come not?
What's its type? Like, I don't get what the issue is.
The infimum of A prime, is that not an atom?
notice what you can do with the bottom element.
It's the
What?
bottom element. Yeah,
It doesn't have to be even an A.
A prime, you don't have to be an A.
yeah, it's only be
Yeah, but see, oh, it's just, what?
A prime doesn't have the bottom element.
Yeah.
Is X an element of A or a subset? Is X an element of A or a subset
Not
of
A
A?
prime.
Oh,
Oh,
It says in the bottom, it's
Yeah.
correct in the slides. A is complete.
oh,
not
sure, A prime is not complete.
Yeah.
yeah.
Right, okay, fine. Sure. Got it.
I'm glad that that's cleared up. So we have a normal ordering in the familiar way. It's going to be reflexive, transitive, and complete. All right.
Not anti-symmetric.
Okay. And we're going to have our averaging axiom, or basically if you think of a given proposition, if it's preferred to another, then the disjunction of those propositions will be intermediate, right, with respect to your preference ordering. And the analogous conditions for indifference defined in the standard way. Now, impartiality is a kind of way of being able to tell when two propositions are equal probable. At least functionally, it gives you that. And this is going to be a little bit of a mouthful. I'll try to say it in the coherent way. Let two elements be part of our algebra, these are non-empty parts of our algebra, where well, you're indifferent between the two, and they're mutually exclusive. Then if you're indifferent between their disjunctions with a third proposition, where their conjunctions with that proposition are also mutually exclusive, right? And you're not indifferent with that third element, right? Between A and C for some other proposition, right? Should that be? Yes. For some proposition, this is true, right?
There exists a C such that.
There exists a C such that, right? It has this relationship to your A and B, right? Then it will be true for every other proposition in your algebra that the disjunction with it and A and B, right, will be an object about which you're indifferent. It's basically saying because the probability and the utility go together, if you happen to satisfy this condition, right, so that these A's and C's are not the same thing, right, you're conjoining something that there might be a nice visual diagram of this. Imagine that the value is influenced by the size of the set, right? You can think of that as the probability of the set. And C is a different size than A. And I conjoin it to each A and B. So the proportion of the total area determined by C matters. Right? If in this setup, the union of A and C and the union of B and C are valued equally, right? Then what you're saying is that, right, A and B are equal probable for you. Right. And then we have a natural continuity axiom that makes sure that our evaluative attitudes are not full of holes and gaps, right? So for every sequence of propositions in our algebra with a defined supremum, then if B is preferred to this defined supremum, which is preferred to C, then there exists an N such that it is also intermediate to those two. Now,
And A star is just the name you're giving to the supremum.
that's right.
Okay.
So for Bolker's representation theorem, what this ensures is in the normal way that we have in each decision framework, that if an agent satisfies axioms 1 through 4, right, then they are representable behaviorally as if they had a utility probability pair with respect to which they're maximizing expected value. Right. Now, this will not tend to be unique, right? And you get not just the normal kind of positive affine transformations of utilities, but you get non-uniqueness of the probability distribution and the pair, and you need kind of further assumptions to get out uniqueness in this framework relative to, say, Savage. You need things like unbounded utilities, right, to ensure that it's all behaves correctly.
So here U is also a signed measure, right?
That's right. Good. So with the machinery set in the background, let's model this value refinement process. Right. And we're going to start with something that looks initially like Joyce, and we're going to extend it. Right. So we said, consider our omniscient agent that has all of her attitudes determined about, right, to kind of an arbitrary degree of precision. So if you just gave her more and more fine-grained, right, elements in her algebra, she's like, I can evaluate that, I can give you probability, I can give you utility, to some arbitrary degree. Right? And this is just to get it in the background so that we can talk about refining toward this ideal agent. All right, her A is her complete volume Boolean algebra. The act partition includes all fine-grained actions, and her probabilities and utilities are defined over the right objects. You can think of her as having considered every relevant factor to an arbitrary degree of precision settled under her valuation of every possible act. Right? Not indefinite degree of precision, to arbitrary degree of precision. She's not done the infinite down thing. She's done enough of it.
Enough of it for what?
For everything that you could care about the decision situation to become. Right. The kind of agent we're interested in has not undergone arbitrary refinement. She has this representation of the decision problem, where we have A naught as a coarse-grained subalgebra of our ideal agent algebra. And her act partition is a maximally fine-grained coarsening of our ideal agent A that is a subset of her subalgebra. So imagine taking this algebra, which is defined to this kind of arbitrary degree, and just maybe this agent is only able to make two distinctions. Right? It's just able to look at the situation and say A not A. And the probability and utility functions are restricted in the appropriate way to this subalgebra. Okay. So this agent now is the kind we want. It's not considered every factor, right? And at least parts of her attitudes are restricted to the factor that she's considered. Right? A binary refinement for this agent, right, is taking an element of her act partition, this thinking through more deeply, how to split the orange, right? How to allocate time with the partner, how to realize the human's values, right? And what you'll do is you'll take that original element of the act and take some kind of heretofore kind of unconsidered proposition, one that's, right, and in particular one that partitions this act. Right.
Because it has to stay a Boolean algebra, this is the only two partitions you can add, or something.
What do you mean?
The only two propositions you can add. I guess like A and B, or and A and not B have to both be added. Then.
Yeah, if you had one, you want to keep it in algebra.
Exactly.
That's right, that's right. Though in general, you'll close this under the proper operations when we get to the algebra.
Okay.
Because of course there's more things that you need to be able to say than these.
Okay.
Right. Good. So visually, we took one of her acts and partitioned it into two parts. And the K-area refinement is just a partition with n, or k elements here. And just an observation, any K-area refinement can be achieved through sequential binary refinement. So we're going to just focus on the binary case throughout and say you can get by carving one piece, turning one thing into two, into turning one thing into n.
So this is like a refinement of like actions. We are getting like a richer action space or something.
That's right. You can think back to that kind of divide the orange, figure out what to do with your partner example.
So for K-area, it seemed like you didn't add the negations of B. Is that right?
Well, they're mutually exclusive.
Okay.
There are partitions.
B2 is not,
Okay,
B2 is not B1 or something.
Each is the negation of the rest.
Sure.
Also, to your earlier point, Abel, if an agent is equipped with a catch-all hypothesis, which is sometimes done in non-parametric space and other contexts, where you just keep a hypothesis, and some of us who like to do applied probabilistic reasoning often have this too, is when you're, say, in a forecasting task, you carve out as much of the sample space as you can manage at a given go, but you'll characteristically have a sense of, and keep the hypothesis, which is nothing I've thought of so far. And in some problems, that might even make up a majority of, the probability measure for you. Like some problems you're like, oh, maybe like I have this sense of it's this small corner of possibility, and other problems you're like, probably it's something I haven't thought of. In that case, if you are the kind of agent that has this sort of a catch-all, you can think of, Joyce's other operation of expansion, which is adding this unconsidered but now articulated possibility to your algebra, as a special case of refinement. I'm carving off a piece of the catch-all, in the appropriate way. Yeah.
Doesn't this require that the total math you put to the new possibility be upper bounded by how much math you put on your catch-all?
That's right. And in general, there's kind of studies on in different sorts of learning situations, what's the sensible fraction of the catch-all to carve out? And if you're in a kind of learning situation where you expect to be getting a command on it, should the relative fraction of the catch-all that you carve out change over time and so on?
But in Joyce's expansion, can't you start with add a new thing which suddenly takes up 90% of your beliefs?
Yeah. That's nice. I think that is a difference. Because with Joyce, he doesn't say anything about the restrictions on what fraction of the belief space this addition takes up. He just says the rest has to scale proportionally. And yeah. So in a sense, if you're doing this catch-all approach, you are a priori kind of restricting the.
Well, but the catch-all is just a label, right? I mean, you can
always scale it after.
Yeah.
You could just combine it with the Joyce.
You could scale it after, is what you're saying. Maybe I just learned something that makes me, Though, of course, we don't have rules about how to. It's not in the math how you deal with the catch-all.
And sometimes the catch-all is a label that kind of semantically means when you refine further, you're going to do it by breaking pieces off the catch-all.
Yeah.
So like you could take a big piece of something else and make it into a catch-all. That's kind of weird, right? Like it's index semantics.
That's right. Yeah.
So I may have missed something here, but have we constrained to precisely Bayesian updating in any way here? Am I allowed to just make Bayesian incoherence updates according to this framework?
So we have to think about something somewhat different here to model the learning experience. In that.
Let me rephrase slightly. Am I allowed to go from 0.1 probability to 99% probability on a single claim?
Yes.
Okay.
Depending on your underlying model, we'll see. It'll be about your attitudes about what that learning experience will look like. Sometimes you expect after you learn, maybe you refine one element of your act and before it was 99%, or it was 95%, and you can actually even go from the probability of this element that I partitioned was like 5%, and it goes up to 95% based on your specification of your expectations. So just to kind of visualize what we said before, it was just what Abel pointed to, you could model expansion, right, even this extreme version of expansion as a refinement of the catch-all, where you could zero out the catch-all. So I think in general, probably you don't want to zero out the catch-all if you're using this as a part of your learning process. Good. So for us, value refinement involves two distinct stages: ex ante uncertainty about refined values, and ex post learning about realized values. Now to do this, we need to model the agent's attitudes toward possible refinements. When you tell them,
Sorry, a couple slides ago, did you put up a paper and then not say anything about it?
oh, this is a nice paper thinking about how to have catch-all hypotheses in non-parametric space.
Subliminal message.
Read the paper. Good. So, to model the agent's attitude toward these possible refinements, we're going to introduce a new probability space, right, where omega here represents one possible realization of the refinement values. Right. So this probability space is about, right, modeling what I expect and what can occur and what I expect to occur when I think through how do we split the orange, when I think through how do we allocate time in our partnership. To do this, we're going to introduce these minimal stochastic extensions that are extensions of our initial probability and utility functions to realizations of not just what we had before in our algebra, but to realizations of the sample space. Right? So we can now reason simultaneously about, I just learned something from refining, and also whatever it was I was thinking about before.
Are we assuming that these two, so P with the wiggle is constructed from the previous P and the blackboard P, and are we assuming that they are independent kind of?
Which are independent?
Because it was constructed from probability over the sigma algebra and the probability over omega. Are we assuming they are independent or not necessarily?
Not necessarily.
Okay.
Let me think. I'll give you the constraints that we have so far that seem natural,
okay,
and then we can think about whether there needs to be dependence or independence. I think you should be able to express, you definitely should be able to in general express dependence in this situation.
Yeah.
I haven't thought about that,
Okay.
but it's very feasible. And then what would the dependence look like? It would be something like if I'm thinking about splitting the orange, given that we have split the orange, I should think about it differently maybe?
Yeah, your probability or your preference over certain refinements depends on some things in the world that might happen or not.
Yeah. I think you should be able to do it. What do we have? Well, we have the kind of coherence requirement that for every element of our original algebra and for any realization, right, you're going to keep the probability of that original element. Okay, so I'll move a little more quickly. Suffice to say, this should be a coherent extension of your previous attitudes. So it should be an extension of the probability function, it's an extension of the utility function, but what we'll actually see is as we relax some of this, you can get your probabilities and your utility to change in a sensible way, right? And we retain measurability for everything, right? So for each element of our algebra that could be refined, we now have this joint distribution, right, over the ways that it could be refined. And in particular, they're going to be over the breaking it up into those two elements, right? The A refined into U and B and U and not B. The utility of each of those new acts available to you, and the conditional probability of the acts. This is also something that we can refine, which is allowing, right, then each to realize a distinct probability so that the sum of the probabilities is different than the original probability you thought about, right? So you can think through different ways we could resolve our marital issues. I've got marital issues in mind. And realize that actually when I've thought it through, they're collectively more or less plausible than when I thought, started thinking about it just so that I could realize they're collectively more or less desirable, right, than I initially expected. And this is just going to be done by realization of random variables in our new sample space, right, where they're going to satisfy all the kind of sensible properties for how you'd expect, right, conditional probabilities to work within this partition. So we're now defining it sensibly, probabilities, utilities over the elements of the partitions. They're realizations of random variables. So as you were mentioning earlier, based on what kind of random variables they are, they could wildly change probabilities and utilities of, right, this refined partition. They could be subtle shifts, or they could be just dramatic shifts that swamp, right, your evaluations about the rest of the algebra. Right. So just giving you a sense of the coherence, I'll leave the example as an exercise to the reader. Right. What constraints should we have now? So now I want to ask you the question, should you refine or not? Right? What would a rational agent be required to do when we're thinking about this kind of a learning experience? Well, one very natural candidate is that if you have your current valuation of a proposition or an act, right, it should be consistent with your expectation of what, right, this bundle would look like if you were to refine it. Something like, if I am doing goal kicks and I kick to the left and I realize more nuanced ways I could kick, a shot to the left should go, then I should expect that when I spelled out those different ways that my shot to the left would go, the value would be equal to what I currently think, right, shooting to the left would be. Why? Why not this? Because if you violated this, you should already evaluate that proposition differently. It'd be kind of weird that you're like, no, you know what, if I spell out the different ways that this could happen, they actually sum up to something different than my current value.
But I thought the whole point was when you start to think more deeply about something, you can come to new realizations.
So I think that's exactly right. It's when you fine grain it, you can take this bundle, which is your average expectation of something, and then you basically use option value to choose out a specific way it could be realized that might be higher in value than the average way it would be realized.
Okay.
Yeah, so you can do better, you won't do worse, because you can pick a subset, basically.
Right.
Now, you won't do worse in expectation.
Yeah,
Okay.
Right? But you can in actuality.
because then you realize random variable.
Right.
Yeah.
You will get a gamble that's at least as good.
Everything is right there.
That's right. Just so. So here's our refinement reflection principle, just for any proposition with potential refinement, right? Your current value for that proposition is going to be your expectation of the proposition under refinement. That is to say, when you partitioned it and you sum over the weighted elements of that partition of the proposition, right? Those should be the same. You shouldn't feel like that thing, in all the ways it could be realized, is better than how I actually evaluate it. Binary refinement is, in the simple case, it just resolves down to this integral over the two elements of the partition. Now, this is, it's very consistent with traditional reflection principles, right? That require our future, our current credences to align with our expectations of our future credences, but instead of it being under a conditioning event, which is the learning experience, it's under a refinement. So, in summary, what does this sort of agent do? When she refines her conceptual space, she realizes a particular refinement given an appropriate probability space of the utilities and probabilities of the elements of the partition of her refinement, right? And these utilities are going to be defined over, each of these in a sensible way. And this triggers a change of her representation of the decision problem, where when she incorporates the refined proposition, notice she has to close under the appropriate operations to get back an algebra. And she has an enriched partition, with those new acts available to it, where their values are given in the normal way, and the original act now is the convex combination in its value of the new act. Know that the reflection refinement principle ensures that in expectation, your act is equal to its refinement. But post-refinement, this will typically not be true. Right? Indeed, we'll see that if you have what we call refinement uncertainty, which is basically you have continuous marginals that are non-degenerate, so they have some variance, they will almost surely not be exactly what you thought they were before. Right? So we're going to have is that refinement uncertainty plus this reflection principle is going to drive a bunch of our results. Maybe I'll give you the results. Maybe I'll give you a quick visual of the results. What happens when we, here's our first theorem. Just as Riff was intuitively anticipating, right? The logic is when you refine, if the refinement is costless, right, then it has a strictly increasing expected value for you, and you have this refinement uncertainty, so continuous non-degenerate marginals. You think it's possible that the refinement, right, yields better value, and the deep intuition for this is this kind of optionality value. When you take something which is an average, you unbundle the elements of the average, right, you will expect there to be something in there which is better than the coarse-grained realization of that object. Right. Visually, you can start here. Your best response is picking the maximum value element. Refine one of those. Now your best response, well, you're in expectation, you have a value of what this is going to be. And that's going to be your choice of the best element of the new partitions. And in general, here, your enriched choice set will have a higher expected value than your original back set. Good. This is going to be monotonic under repeated refinements. But we can talk about under the appropriate sorts of like diminishing marginal return to refinement. So now you have costly refinement. The answer to what to do, whether to refine or not, is if the cost of refinement is too high, is higher than your expected marginal gain, never refine.
So
if it's sufficiently low,
also out of time.
if it's sufficiently low, go until it's not worth it anymore. Take care all.
The good question, but this refinement is like it will not change like the value of propositions under the same coarse gradient, right? So it's like if you refine the proposition and then you aggregate it again, then its infinity is the same.
Yeah. What is the same?
Like if you have A and you refine it to A and B and A
the value change, but you do expect the
not B,
something that's higher value. It's not guaranteed.
So how can it go down?
It could go down if you think about like I go left and then you discover you're like